welcome once again to Calculus 2 with Dr. Strand. So this is the third and final video of our exploration with polar coordinates. And today we're just going to kind of summarize and review what we've looked at so far. So the things that we're going to do with polar coordinates are just be familiar with the coordinate system, the basics of it, know how to plot and understand polar functions, and then how to calculate area. So those are the three things that we're going to look at again today. And one of my favorite ways to do this is to try to match rectangular graphs with polar graphs. I think this is a great way to make sure that we understand what we're trying to do here. So what I'm going to give you are 4 rectangular graphs here and 4 polar graphs, and I want you to pause the video and take a few minutes to try and match them up. And one of the things I want to make sure we do is plot a couple of reference points. So make sure that we can understand what points in Cartesian coordinates correspond to on a polar graph. So go ahead and pause the video and try to figure out which of these rectangular functions matches which of these polar functions. Okay, so as I mentioned, one slick way to do this is to find points that correspond between the rectangular graphs on the left and the polar graphs on the right. But another way to do that is to get comfortable figuring out what these loops correspond to on rectangular graphs. That's actually a pretty easy way to tell what's going on. So we're going to use both of those strategies depending on the function. So for example, let's just start with this function here, I. So I, when theta is 0, starts at 1. And it turns out that there's actually only one graph that starts at 1 with an angle of theta. And so what we want to do is see which one that is. And the scale is looking weird to me. So one thing to notice is that to make this fit on the slides, the pictures are rather small. But one thing that you can do is you can zoom in these as much as you want and they stay nice and sharp. And so I would recommend doing that. So for example, let's see, so 1 is actually this point here. So it's hard to tell when you're zoomed out, but this solid radius, oh, I'm gesturing with a mouse that maybe you can't see, sorry. This solid line here is at 3, so this solid line is 2, and this solid line is 1. Okay, so right here we have the only graph that intersects when the angle is 0, we're at a radius of 1. So let's zoom back out. Probably never going to be able to find the regular size anymore, but that's okay. Okay, so what we're looking at here is this point is at 1, and there's no other graph that has that. But let's just look at the rest of it to make sure it matches. So when we are down at pi over 2, we are going to be at a radius of -1. So pi over 2 is this angle here on the graph, and the radius is down at -1. So we're going to say that this has got to be graph A. That seems pretty clear. Okay. So the next one, I don't know how you want to do this. If there's other things that line up, you're certainly welcome to do this in any order. I'm just going to go on to. So rectangular graph 2 starts at 0. And again, it looks like there's probably only one graph that does that. It looks like it might be D here. But let's look at some of the other evidence to make sure. So as I mentioned, another thing that's useful is figuring out what these loops correspond to. And so what you should think of is these are places where the radius goes from 0 out to some distance and then back to 0. So what we want to see is, do any of these graphs, right, as we start at 0, go out to some distance and then back to 0 by the time we are at this vertical line? And again, it turns out that yes, there is, it's this one. By the time we are at pi over 2, this has made a loop. It's gone from 0 out to some radius and back to 0. And so, you know, you can kind of think of this loop corresponds to this loop. And then where is this one in the graph, actually? So since the radius is negative, remember this range is pi over 2 to pi. So that means we're sweeping out this angle here, but because the radius is negative, we're actually drawing it down here. So that corresponds to this loop. Okay, so you can do a similar investigation for the rest of those loops, which means this is most likely going to be D. Okay, so let me clear all this out. So far we've identified probably A and D. Feel pretty good about that. So if we do a similar evaluation on the third rectangular graph here, we see that this graph actually starts at -1 when the angle is 0, which corresponds to that point right there. So again, using key points can be pretty slick way to figure out which graph is which. And it turns out that, let's see, as we sweep out, let's see, what is this? So this angle is somewhat before pi over 2. So the radius is negative. We're going to be sweeping out that loop there. And then this region on the rectangular graph corresponds to now the big loop that starts just before pi over 2, and then we sweep it out and we finish sweeping it out just before, well, somewhere just past 3 pi over 2, right? So that right there. I'm sorry, what I said at the beginning was wrong. This first thing doesn't correspond to a loop. What this is going to do is going to, okay, let's erase this because I misspoke. The way this graph gets traced out, this is important to think about. The way this graph gets traced out is we are starting here and we go from a radius of -1 to 0. So that means that's this region here gets swept out first. And then now the radius is positive once we hit, you know, somewhere around here, this angle. And then we sweep out the graph, and then we get to 0 sometime around here. And then now the radius is negative. So in this region of the angle, we're actually drawing this part of the graph. Okay. So we know this should be A, D, C, which means by process of elimination, we hope that this graph corresponds to B. And again, I think one way to look at this is that these loops correspond to loops on the polar graph. And so we get a, so let me back this up a little bit. This first one here is a half loop, right? It starts at a radius of 2 and goes down to 0, and that happens to be this right here, this half loop. And then, so this is kind of fun trying to think about it. So now the radius is negative. So the way we're going to trace this graph out is going to look like this. It's really quite beautiful if you can figure out a way to watch it get graphed. Okay, so that's kind of our basics of polar functions and coordinates. I feel like this is a pretty good, this exercise is a pretty good review of the basics of the polar coordinate system. You have to know how coordinates work and how polar functions work to be able to match these effectively. And again, we didn't really write down specific points, but you should make a note of specific points and where they correspond. Okay, so the next thing we want to do is we want to also look at, oh, and then I put a little answer key in there too that matches what we talked through. I want to look at, again, some area problems to practice this newfound skill. So we've seen these functions before, but the shaded regions we're interested in are a little bit different. So I'd like you again to pause the video and take a crack at setting up the integral to find the area of the shaded region. This one is actually kind of fun because it looks like you need to calculate the difference between two areas at first glance. But it turns out that that is actually not the case. Because if you draw this, actually let me draw that line again, but I'm going to switch to red so we can see this. If you draw this line, the area that we're interested in is actually just the area from the origin out to the red circle. It doesn't really have anything to do with this kind of cloverleaf loop. And then there's this point where the two graphs intersect, this angle. And then after that, so once we're past that, when we draw a line here, we're actually only going out to the blue curve. So we actually don't need the red circle at all once we pass this point. So it turns out that in this case, what we're going to be interested in is what is that point of intersection, and then we're just going to set up two separate integrals to calculate this area. So again, I think we calculated this in the last video. The intersection we can set up as for what angle do the graphs of 1/2 and cosine 2 theta have the same radius, right? And so it turns out that that's got to be when theta is pi over 6. So what we get to do here is we get to set up one integral from 0 to pi over 6 of just the circle. Actually, it doesn't have anything to do with that cosine curve. And the other area that we're interested in, I guess we need to kind of know when the cosine curve gets down to 0, right? Is the thing we need to know, but that's going to be at pi over 4. So algebraically, what I just figured out was if we need to know when the cosine of 2 theta is going to be 0, well, that's when the angle that we're looking at in cosine is equal to pi over 2. That's the first time cosine is 0. So that means theta's got to be pi, oh, not 4 over 4. Theta's got to be pi over 4. So the second integral is just the integral of, so we mark this kind of line where they intersect, and we're going to go from that line, so from pi over 6 until the graph hits 0, which is at pi over 4. And now we're looking at the area between the polar curve cosine of 2 theta and the origin. So we integrate 1/2 cosine of 2 theta quantity squared d theta. All right, and the sum of those two integrals will give us the area of the shaded region that we're interested in. And again, I think I calculated this. Nope, I didn't. I'm a liar. Okay, great. Set up the integrals and we're good to go. All right, one more. I would like you again to pause the video and try to find the area of the shaded region. So in this case, this one is actually a little bit tricky because finding the angle bounds is a little bit weird. It looks at first, no, it does. It looks at first like we're going to have to do subtraction, and it turns out that that's correct. So if we, again, I'm going to draw a red line for a little bit of a contrast here. We are going to, if you draw that out, right, there's a sweeping out of this area, and then that's this region here, and then we're going to have to subtract the region down here in that little bubble. So again, we need to find what angles are going to determine that region. So let's see. So again, the rectangular graph is going to be pretty helpful to have here, so I'm just going to sketch it again. Since it's not too hard to get a really rough sketch of what this is doing. We have 2 pi, pi, and 3 pi over 2, and pi over 2. So the graph is going to be here and here and here and roughly here. Okay, so the graph is going to do something like this. And again, we could look at it on Desmos to kind of play with. Actually, let's go ahead and do that. That's a good idea. Let's do this one on Desmos just because we haven't used Desmos in the last two videos. So just as a reminder, you can graph these polar functions, but we're not going to do that this time. We're just going to look at this as if it was a rectangular function. So we are looking at 1 plus 2, and I'm going to put cosine of x here. And we are really only interested in x going from 0 to 2 pi. So this is the part of the graph that we're going to look at. And I'm going to put it in presentation mode so we can kind of see what we mean. The regions that we're interested in. Okay. Oh, and I wonder if I can easily mark the graph with pi. No, not really. Okay, well, in any case, we can switch back to doing this. So what do we need to know? We need to know, let's switch back to the picture. So we're trying to find where this region is, right? Like, what are we sweeping out for the big one? And then I think the more challenging, because it really looks like it's from 0 to pi over 4 on the graph. So we'll make sure, or we'll actually be able to take that. So this matches up with the graph here, with the grid, the polar grid that we have. So we know that the first integral we're going to integrate is just going to be the function from 0 to pi over 4 of 1/2 times 1 plus 2 cos theta squared d theta, right? Okay, and then what we're going to need to do is subtract some other integral. And in fact, it's not really that mysterious. It's basically the same integral, but we have to figure out different bounds because this second loop is traced out with different angles. So that's what we need to know. That's where I should put the question marks. What are these angles that we're going to use to describe that inner loop that we need to subtract? Okay. So really what we need to figure out is what region or what values of theta are doing that. And again, I think it gets a little bit hard to see there on the cyan color. So let's make this red. So this region here is what we want to try to figure out. Like, where is that happening? So basically, yeah, let's look back at the other graph and see if we can see where that is, right? So we want to trace out a part of the loop, a part of that little loop. So if we go back to the graph, we can see here that these are the bounds of the little loop, right? These points where the graph hits 0. And I think we figured this out in the last video, but we can look at this again. So those points are going to determine what that little loop is. And now that I'm looking at this, it probably is going to be a little bit easier to do this if we had things in terms of pi. So we might not want to use Desmos for this after all. It's nice to get the shape, but it's a little easier to have these things in terms of pi. So we might just draw this again. All right, so what we have is the graph here goes like this. 3, oh, whoops. Oh, no, sorry. So it goes like this, right? We're interested in these points. So that's going to be when 1 plus 2 cos theta is 0, which is when cos theta is equal to -1/2, which we figured out last time happens at 2 pi over 3 is the first time. Okay, so that's where the loop starts, but really what we want is when the loop is here. So that's actually this point down here, right? When the graph is at -1, that's right at pi. Okay, so that's cool. All right, so that's pi. That's where that happens. And then it actually looks like it doesn't quite make it to 0 here. So I bet that what we want is this angle here. So it's the, so what is that going to be? So this is pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. So this is 5 pi over 4. Right, so at 5 pi over 4, we haven't gotten to 4 pi over 3 yet. So let's see, yeah. 5 pi over 4 is like right here somewhere. So the radius is still negative. And yeah, and that's going to get us what we want to do. So what that means is this second integral that we're going to subtract is going to be the integral from, where did we say we wanted it? Was at pi. Pi and -1 is where this curve starts, and it's going to go to 5 pi over 4. And again, we're integrating the same function, so we're going to be looking at 1/2 times 1 plus 2 cos theta quantity squared. That's the area we have to subtract, and so putting that all together, we do have, we start it from 0 to pi over 4, we get the big area, and then we subtract the little loop by integrating the same curve, the same polar function from pi up to 5 pi over 4. All right, so just as by way of review, the things that I expect you to be able to do with polar coordinates are use the polar coordinate system. So understand how we talk about points in the plane and how to kind of go back and forth between Cartesian and polar points. And then the second thing I expect you to be able to do is talk about graphs and understand graphs. And again, the big difference is graphs in polar we think of as going from the origin out to some radius rather than, you know, x and y coordinates. And then the last thing that I expect you to be able to do is set up integrals to calculate the area of shaded regions. And the tricky thing there is figuring out the angles that sweep out these things. And the rectangular graph is usually pretty helpful for that. All right, that concludes our exploration of polar coordinates, polar functions, and polar area. I hope you had as much fun as me. I don't know if that's possible, but hopefully close. And tune in next time for the next topic. Oh, that's a fun surprise. All right, well, we'll see you all later.